Hi friends, welcome back. Today we are going to solve one very important graph coding problem that is previously asked by big tech companies such as Google, Facebook. It's on Leetcode. It's 2192, all ancestors of a node in a directed acyclic graph. So this is of a medium complexity and this is a very important coding problem that is for graphs. So if you are preparing for any Java J2E coding interviews, then please make sure you watch this video until the end and understand this problem completely, because this is a very important coding problem and recently asked by many big tech companies. Before we start looking into the problem details, I just want to mention that my channel is dedicated to help people in their Java J2E and coding interviews. On my channel, you will find lots of helpful videos that can help you in your Java and coding interview preparation. There are over 400 different varieties of solved problems shown in the videos, explained with whiteboarding session, examples and Java code for your easier understanding. So if you are preparing for any Java J2 interviews or coding interviews, or simply want to learn new Java concepts, then this channel can definitely help you in learning and and in helping you in understanding how to solve different coding problems. So please subscribe to the channel now. So let's start with this Leetcode 2192, all ancestors of a node in a directed acyclic graph. So from the title itself, you will see that it's a directed graph and it's a acyclic graph, right? So there is no cycle in the graph and the edges are directed, right? So let's start with this. So you are given a positive integer n representing number of nodes in directed acyclic graph DAG. The nodes are numbered from 0 to n minus 1 inclusive. So you are also given a 2D integer array edges where edges of I is from to 2, denotes that there is a unidirectional edge from to 2 in a graph, right? So it is a unidirectional edge. So it means that it goes from to 2, right? And not a vice versa, right? Only it goes from to 2, right? That's why it is a unidirectional edge. Return a list answer where answer I is the list of ancestors of the ith node sorted in ascending order. So this is what we have to return as the answer of this problem. A node U is an ancestor of another node V if U can reach V via a set of edges. So what that means is they have given us some example here. So for example, let's just first understand what this means. So I'll just show you in the whiteboard so it's easy to draw here. So what it means basically is, for example, if you are looking at 6, right? So 6 ancestor, direct ancestor can be 3 and 4, correct? So 6 direct ancestor can be 3 and 4, correct? Because you can reach to 6 by 3 and 4 directly, but we have to capture all the ancestors. Then we have to also go and capture the ancestors of 3, because you can reach 3 from 0 as well as 1, right? And you can reach 4 by 2, correct? So we have to capture all these ancestors. When we are answering who is the ancestor of 6, then we should say that 0 1 2 3 4, correct? Because we have to answer that in a sorted order, right? So that's what the problem is basically. So they have given us these two examples, and the constraint says that the n is between 1 to 1000, right? And the edges dot length is the minimum of 2000 and n into n minus 1 divided by 2. So if n is like very large number, then it can be minimum of these values, right? So it can be very big basically, right? So maximum you can say that it can go to 2000, right? Because we have to we are choosing the minimum value between these values. So 2000 edges is quite a large graph, and edges, every edge will be having from to 2, right? So every edges length will be 2, and from and to will go from 0 to n minus 1 inclusive, and from is not equal to 2, right? So they have already told us this here. And there are no duplicate edges, and it's a directed and acyclic graph. So this is already given to us, right? So we don't have to worry about these things, that cycle and all that, because it's already given to us. So let's take a look at this first example, and first we will understand how we can, like, what the problem is. So I already explained you one example where who is the ancestor of 6. So we will say 0 1 2 3 4. So let's see, this is the given input and this is the output. So 0 1 2 3 4 5 6. So this one is the for node 6, right? So this is for node 6. So we are saying 0 1 2 3 4, correct? 0 1 2 3 4, because we will have to capture all the ancestors, not just the immediate one, right? So all the nodes, how it will work, because we can reach to 6 from 0 1 2 3 and 4 all, right? How we can reach from 0 0 to 3 and 3 to 6, we can reach from 1 1 to 3 3 to 6, we can reach from 2 2 through 2 to 4 4 to 6, right? And 3 to 6 and 4 to 6 we can directly reach, right? So that's why we have to capture all these nodes as a ancestors, right, for sixth node, right? How about 7? So these are all the ancestors for the seventh node, right? 0 1 2 3. And why? Because to 7 we can directly reach from 2, correct? And we can also reach to 7 by 3, right? From here we can directly go, but now at 3 we can also go from 0 and 1, right? So we have to capture all this in ascending order. So how it will work? 0 1 2 3, right? 0 1 2 3, right? So this is what we visually we can solve this problem, but as you see the graph can be very big. We have to find out a algorithm how we can solve this graph using Java, right? So let's take a look at like the logic how we can solve this problem, right? So we will go through this input that is given to us, number of node is given and edges are given, right? So we will form all these values from this, right? We will first form all these values. So from to 2 we will form, and then 2 to from we will form, and we will also capture the degree or in degree of each node, right? So what is a from to 2, right? So it means that from this particular node, which node I can directly reach, that's what it is saying basically. So we will capture this value when we are traversing, when we will process this edges list or input edges list, right? For example, 0 I can directly go to 3 4, right? 0 I can go to 3 and I can go to 4, correct? So we will capture this relationship here in the from to, right? From 1 where I can go directly to 3 I can go directly, right? From 1 like this. Then from 2 where I can go 4 and 7 I can go from 2, right? Like this, right? From 3 where I can go 5 6 7, right? How? As this is the 3, right? 5 6 7 we can directly, because we have edges that directly goes to 5 6 7, and for from 4 we can go to 6, from 4 we can go to 6. So this is the one thing we will get when we are processing the edges. The second thing we have to find out is to and to from, like in a reverse direction now, right? What we have done, now we will do it in reverse direction. So it means that where, like from which node I can come to this 3 node, right? Directly from which node I can come to the 3 node. So I can come from 0 and 1 to the node 3, right? So we will define this we will also populate this relationship in the to from, right? So for example 4 where we can directly from which node we can directly go to 4, right? So 0 I can go to 4, 2 I can go to 4, right? So 0 and 2 like this basically, correct? So for 5 it is 3, as you can see. For 5 I can go from 3 to 5 directly. Then for 6 I can go from 3 to 6, sorry, 3 and 4, right? 3 to 6 I can go, and 4 to 6 I can go, right? And for 7 I can go from 3 and 2, right? For 7 I can go from 2 and 3, right? So these things we will populate when we are processing the edges list that is given to us as the input, and at the same time also we will also capture the degree or in degree, right? So what does degree or in degree mean? So degree or in degree is basically how many arrows are coming into that node is the degree. So how many arrows are coming into node 0? 0 arrows are coming. So this zeros in degree is 0. For 1 the in degree is 0, correct? For 1 also in degree is 0. For 2 also in degree 0, because there is no arrow which is coming to that node, right? Now for how many nodes are like arrows are coming in node 3? 2, right? So we will capture that here. Same thing for 4. 4 also 2 arrows are coming, right? Incoming. Then for 5 1 arrow is incoming, right? You can see it here. For 6 2 arrows are incoming, and for 7 2 arrows are incoming. So we'll populate this degrees array basically, right? by using this given information. So now we already have the in degree also, correct? So what after that what we will do is we will use the approach called as BFS or breadth first search, right? Breadth first search we will use, right? Or breadth first traversal we will use, right? This is a very important technique for graphs, so you must know this BFS approach, right? So you can easily solve these problems, also called as topological sort. So how we will do it? So we will start with the nodes which has in degree 0. So which are the nodes at in degree 0? 0 is in degree 0, 1 is in degree 0, 2 is in degree 0, right? So what we will do is we will put that into our queue. BFS always uses a queue, right? So let's assume that this is our queue, right? Queue is implemented by using linked list in Java. So we will first start putting the nodes which has in degree 0. So which has in degree 0, 0, then 1 and 2. So all these nodes has in degree 0. So we'll put that into the queue, and then in the next iteration of BFS we will take it out, like we'll take out 0, right? And then what we will do, we will capture its children, correct? So 3 and 4 are the children of 2. So we will capture its children and we will reduce its in degree, right? So now 3's in degree is 2, correct, in the beginning. So we will reduce it by 1 basically. So now 3's in degree will become 1, right? And 4 in degree will also become 1, right? Because we are reducing it by 1, right? Because those are the children of 0. So we will do that. And if the in degree becomes 0, we will add it to queue. So it's not becoming 0, right? It is 1, so we will not add it to queue. So after 0 we will process 1. So when we are processing 1, we will again decrease the in degree of 3, right? Because 3 is child of 1, like 3 has a like a ending edge from 1, right? So we will reduce the in degree of 3. So now the in degree of 3 is 1, so it will be reduced to 0 now, correct? So it will be reduced to 0, I am writing here. So once it becomes 0, we will add it to our queue, right? So we will add it to our queue. And at the same time, when we are processing this information, we will use our this from to and to from information, right? These two things we will use that we have already populated to understand what are the like ancestor of 3, right? So the ancestor of 3 is 0 and 1, right? So ancestor of 3 is 0 and 1. So let me just write down somewhere. So let's say here I'll just write down. So ancestor of 3 is 0 and 1, correct? 0 comma 1 we found, right, with this information. Now we processed 1, now we will process 2. So 2, when we are processing 2, we will reduce the in degree of 4, right? So in degree of 4 will become, so it is 1, so now it will become 0. As soon as it becomes 0, we will add that into our queue, right? So we have processed 0, 1, 2 in this iteration, right? Because the size was 3, we'll get the size of the queue in the beginning, so we know that how many elements we want to process in that iteration of the BFS, right? So we are actually we have processed 3, and so after this, when we are processing 4, again we will know what are the direct ancestor of 4. So direct ancestor is 2, right, for 4. So direct ancestor is 2, so we'll capture that here, right? So this one we will keep it as a set. So this is a set basically, right? This is a set, right? So after that, in the next iteration, we will take out like 3. When we are taking out 3, we will again process the like its neighbor, right? 5, 6 and 7 we will process. So the in degree will be reduced by 1, right? So 5 in degree will become 0. So once in degree becomes 0, we will add it into our queue, correct? So we will add it to the queue. So now 5 we added here. So 6 also in degree will be reduced by 1, so it becomes 1. For 7 also it's reduced by 1, so it becomes 1. And also we will capture who are the ancestor for this node 5, right? When we process 5, what we will do is we will when we are processing 5, what we will do is 3 is the ancestor of 5, right? Because directly we can go to 5 from 3, but who is the ancestor of 3? We will add this 3 into that. So ancestor of 3 is 0, 1. So what we will do is 0, 1, and then we will add this 3, to the ancestor of 5, right? So we get all the ancestors, and that's how we will solve this problem, right? Because for each node we know what are the ancestors, right? So for example, when we are processing for node 5, we have to check which are the ancestor for node 3, right? So 0 and 1 are ancestors for node 3, so we will add these 3 additional into that, right? So 0, 1 and 3, so these are all the ancestor of node 5, right? So similarly for node 6 also, who are the ancestors of node 6? Then whoever is the ancestor of 3 plus 4, right? And then like, so basically 3 means who is the ancestor of 3? 0 and 1, right? So 0, 1 we will put here, correct? 0, 1, then who is then 3, right? Because 3 is directly ancestor that we can come here, right? Then 4, and 4 we can come from 2, right? So all these we will find out here basically. So these are, because we are using set, so we will use add all method of the set. So whatever directly we can go from to 6, we will get the set of ancestors, right? So when we are answering that who is ancestor of 6, we will say that 3 and 4 plus ancestors of 3 and ancestors of 4, right? So that's how we will answer it. So we will get the complete list of ancestors, and at the end what we will do is we'll go through all these lists and we'll just sort it out, right? Because sorting is required because they want us to give the order in the ascending order, right? So for example, this is not an ascending order, so we have to sort these things, correct? So this is what our approach is, topological sort, to solve this all ancestors of a node problem. So I think you got the idea of how we will first populate this from to from and degree. All these things will populate from the edges list that is given to us, and then we will use the BFS approach and the queue that I mentioned you here, and that's how we will create our answer, right? So let's go ahead and take a look at the Java solution now. So first we created the from to from and degree here, right? So we define all these things. So now all are maps, right? So from to is integer comma list of integer, right? Because it can have multiple values, as you can see, right? 0 can have multiple values, right? 1 can have multiple or 2 can have multiple values. So this is a list basically, right? So same thing from to from also. So to from also is integer comma list of integer. So key is integer and value is list of integer, correct? And for degree is just like integer comma integer, right? Because every node degree is an integer. So this is how we will just create a map. So we have created 3 maps. Here we are going through the input edges array and we are populating our to from to and degree, right? So after we are done with this for loop, we will get all these things populated, right? From to from and degree, all these 3 things got populated. Now we are going to check who are the nodes with degree 0, right? For example, these 3 nodes are with degree 0, so those are the nodes that we can add into our BFS queue, so we can start doing the BFS, right? So that's what we will do. So for that, so we created a queue here, which is just a new linked list, right? And it's of type integer, and here the ancestors map is created. So as you can see, the map is how the map is, key is integer here and the value is set of integers, right? So ancestors is a set, right? So that's how we can use the value. So we can do the sets add all method basically, right? Down the line I'll show you that. So here we are going from 0 to n, we are going through all the nodes and we are capturing all the nodes which are degree 0, right? If its degree is 0, then we are going to add it to the queue, right? So that we can start doing the BFS, and here our BFS starts, right? And our BFS will keep continuing until queue has some elements in it, right? So first we are removing the element from the queue. For example, 0, we removed 0 from the queue, right? And then we will just create one result which is set of integers, right? It's just a hash set, and we will use that to from like map, right? To from map we will use to find out who are the ancestors of 0. So 0 does not have any ancestor, right? Because 0, as you can see, 0 does not have any incoming edges. It does not have any ancestor, right? And same thing you are seeing here also in the output, right? 0, 1, 2. So all these three does not have any ancestor, right? So in that case it will be just an empty set, right? uh, let's take a look at some other thing like 3, for example 3, right? So when we are processing 3, we will find out we will use this information, who are the ancestors for 3, 0 and 1, right? So 0 and 1 we will add here, right? So we will use that to from map to find out who are the ancestors, right? And then we will add that ancestors into our result set. And what we are doing here, this is the add all method that I was talking about. We will get the the previous ancestors, right? And we will add that ancestor into our current ancestor, right? So result, we already added our immediate ancestor here. Now we are adding the previous ancestors, right? For example, let's say for 6, right? Let me just remove like this, lot of colors are there. So let me just yeah, clear some colors here. So for example, when we are checking for 6, right, we will add the ancestor as 3 and 4, right? We will add 3 and 4 as the ancestor, but at the same time after that we are going to add ancestors of 3 also, right? So 0 and 1. So when we are saying who is the ancestor of 6, we will add 3 comma 4, right? But then we will also have to add who is the ancestors of 3, 0 and 1, right? So 0 and 1 also we will add, and who is the ancestor of 4, 2 is also ancestor of 4, so 2 also we will add here, right? So that's what we are doing here basically. This result dot add all will do that here, right? Because the for the current ancestor here, right, we will find out who are the ancestor for that node. For example, in this case we are finding out who is the ancestor of 3, who is ancestor of 4, to answer who is the ancestor of 6, correct? So that's what we are doing here. So after this one is done, then we'll just add our this into our actual ancestors map, right, that we created. This is our ancestors map we will add, right? U comma result. U is the current node that we are processing, and result is the set that we have gotten by using this information, right? So it will give us all the, so result will contain all the ancestors, right? But they are not sorted yet. They are not sorted, right? That we will do the sorting later. So you have to just remember that result will contain all the ancestors, but they might not be sorted, right? After that, what we are doing here is we will go through all these elements, right? Like for example 3 and 4, and we will reduce the in degree, right, what we have processed basically, right? So let's say once we process the 0, and once we process 0, we will reduce the in degree of 3, right? So in degree of 3 was 2 before, so now it will become 1. And once we process 1, then in degree of 3 will again reduce by 1, so it will become 0. Once it becomes 0, we will add it to the queue, correct? So we will use that logic and topological sort of and logic of in degree to decide if we can add that element to process into the queue or not, right? So we will keep reducing the in degree first, that we are doing here. So we are reducing the in degree by 1, and we are checking if the in degree becomes 0, we will add it to the queue, correct, for processing in the BFS, right? So this way we will process all the nodes using the BFS, right? And then we will get our ancestors map ready. So now the only thing we have to do is, we have this set but it's not sorted, so we will have to sort it out. So that's what we are going to do here. So we will create one list of integer, which is expected output of this function, called it as sorted results, right? So it's just an array list, right? So it's a list of integer. Then we'll go from 0 to n, because we have n number of nodes, right? And then we will, for each ancestor we will get the result, and we are going to sort that result basically, correct? So this one will give us the sorted thing, this whole thing basically, right? We are using collections.sort method. So it will sort our list, like the sorted list will be sorted here in this collection.sort, and after it is sorted we will just add that into our sorted results, right? So this way we will get always the sorted results, right? So for each node we will get the sorted result, correct? So for 0 we will get sorted, then 1 we will get sorted. So for all nodes we will get the sorted results, right? As you can see here. So for example, you can see here, right? This is a sorted 0 1 2 3 4, or 0 1 2 3 is also sorted. So this way we can solve this problem with this approach. So let's go ahead and take a look at some test cases. So this is the first test case. Let's go ahead and execute our code snippet. So yeah, so there is no difference. Our solution is getting accepted with this test case. Let's do the another test case, the second example that they gave us, right? So this is the second example we are running now. So second example also is getting accepted, right? So let's go ahead and submit this solution now. So our solution got accepted by Leetcode. It is 88% faster than in performance than other solutions, and 90% faster on the memory usage, which is very good solution. So this is the way we can solve all ancestors of a node in a directed acyclic graph problem 2192 on Leetcode of medium complexity. Very important graph problem. If you are preparing for coding interviews, make sure you understand this problem and practice this problem. This problem is quite recently asked by many big tech companies. It's an important graph problem. If you are new to my channel, there is a dedicated playlist on my channel called as Leetcode and Leetcode Solutions. There are over 250 different varieties of solved coding problems in the playlist that are taken from previously asked coding interview questions by Google, Facebook, Amazon, Apple, Microsoft, Yahoo, and many other big companies. So if you are preparing for any Java coding interviews, then you please go through that playlist. It has lots of good varieties of problems. If you want to practice more problems, then I would recommend 3 more playlists on my channel. The names are Code Forces, Code Chef, and AdCoder. All in all, you will get more than 400 different varieties of solved problems explained with whiteboarding session, as we just did in this case, examples and Java code for your easier grasping and understanding of the problems. So you can understand how we can use different varieties of techniques to solve different problems, right? So if you like this video, if you find this video helpful, and if you like the way the video has been created with whiteboarding session, examples, and Java code, then please give it a thumbs up or give it a like to the video. Subscribe to the channel. Your subscription to the channel is really important for the channel, because that is the way the videos can reach to more people who need help in solving coding problems. One of the main goal of the channel is to help as many people as possible by showing them how we can solve how we can use different techniques to solve different varieties of problems using Java, and how we can use different data structures, APIs, and libraries of Java to solve different varieties of coding problems. So if you like this video, please give it a like, share this video with your friends and colleagues, so they can also watch these videos and get benefited by these videos. If you have any questions related to this problem or this video, then please put your questions below the description section. The Java solution code that we have seen in this session, I am going to post this code on my GitHub account and give you the link. You can check it out from my GitHub project and play with the code, understand the code with different test cases. And if you like my Java solutions, please consider giving it a star to the GitHub project. That would be helpful. So if you are learning Java or preparing for interviews, then keep practicing different varieties of problems. Also, when you are practicing, don't use the IDs. Try to handwrite the code so you will remember the APIs, because many times nowadays they are asking us to write the code on the whiteboard. So make sure you can write a handwritten code, and watch all the related videos. You can get more and better preparation. And thanks for watching this video.